Up in the northeastern part of Florida Bay, there's kind of a haliduli community, very thin-bladed seagrass. Out north of Marathon, there's a very dense syringodium community. Out in the deep water, there actually are ephemeral but very, very large Halophila meadows that don't show up on anybody's maps. And then most of the South Florida is known for the occurrence of turtle grass. It's usually considered to be the most common grass, but it really isn't the most widely spatially distributed. And we have seagrass growing everywhere that at least 10% of light reaches the bottom, except where there's things like corals coming out of the bottom, because seagrasses don't do well where corals grow. So we were asked, beginning in 1995, to define the status and trends of seagrasses in the Florida Keys National Marine Sanctuary. I'm going to talk about that program first and then talk about Penny and Brad's program after that. Basically, how important are they, where are they, and how are they changing through time? And although I'm not going to go through all these points today, let me point out a couple of things. Monitoring programs can only exist for long periods of time if they are based on predefined management, if they're predefined management-oriented goals. So in South Florida, we were about water quality affecting seagrass distribution. Therefore, we designed a program that was designed to look at both water quality, early indicators of water quality, and the status of seagrasses. And that required us to have these explicit models of system behavior that tell us what to measure. And I'm not going to tell you about all our stable carbon, nitrogen, stable nitrogen, carbon, nitrogen, phosphorus analyses that we do specifically because those are tied to our models of how the system changes with respect to the water management goal, and that's controlling water quality. And another thing we're looking at is species composition, because we know that the faster growing seagrasses do better if there's higher nutrient availability. So that's all very important. We have to be precise enough so that we can see change detection, but they also have to be robust enough, because I've had over 110 graduate students involved in collecting data on this project over the years. So if you're the only person in the world with the expertise to measure something, that thing that you can measure is probably not a good thing to be included in a monitoring program, because hopefully the program will survive you. You have to be statistical defensible. And then here's something that I'm not going to talk much about today, but really monitoring programs that just watch the resource disappear are of limited value. What we really want is a monitoring program that will give us characteristics of the system that can help us predict how the system will change in the future before we get big changes in the system. When I have an hour, I'll tell you about how we're doing that, but I won't today. So we started off using the EMAP protocol and polygons to randomly place points across South Florida, and we started diving to figure out where seagrasses were. So this is Thalassia density from 96, and Thalassia density from 97, and Thalassia density from 98. And you see where we sampled changes, so you're seeing changes in the green shape, but that's really not temporal change. That's because there's small-scale spatial change. Then here's the map from 99. Here's the map from 200, and if we put them all together, we get this envelope the distribution of Thalassia in the Florida Keys National Marine Sanctuary. And let me point out that this is all Thalassia as well, and so is this, but those are monitored in a different program. So the first thing we did is we went to find out where all the seagrass was. And so we found out that that's the distribution of Thalassia. Syringodium actually has this different kind of distribution. It's largely absent in the shallow waters. North of the Keys, it's very dense, and you get quite a bit of it out towards the reef tract. It requires more nutrients than Thalassia does. Halophila decipiens, we've discovered there's about 9,000 square kilometers of that out in the deeper water in the southwest Florida shelf. And this is Haliduli wrightii. And we also collect water quality at all these sites, so we have an idea then how water quality determines what species are found where. So when you put all those together and you develop the envelope of seagrass distribution in South Florida, you get about 18,000 square kilometers. So that's really big. That's the size of the state of Connecticut. And Amber just showed you these data, but I just converted them into square kilometers. And so in South Florida, from mapped polygons, these are the data that go into the sim, they can get about 6,558 square kilometers of seagrasses in the same area that we've done this probabilistic sampling, and we've gone to areas that the seagrasses don't show up in aerial photos. So we're getting that there's about 18,000 square kilometers in this area that they think it's about 7,000. So even in Florida, where we have the best programs and the best resources, we're still underestimating the true distribution of these resources. And we're underestimating it especially where they're deep, and the deep areas are the ones that are likely to be the most sensitive to change. Sorry. All right. So we also have a bunch of permanent transects. These stations were established in mostly in 1995. So we've done this broad scale sampling, but we also want to have temporal sensitivity. So we then have permanent sites as well. And just want to show you the type of data that we're collecting from them by bringing up the point that Irma was not the first hurricane to hit the Florida Keys since 1995. And these are data from just a couple of our sites. This is site 216, which is up by Carey's Fort Reef, and this is 243, which is about Long Key. And what you see is all of these are 3 different ways of measuring the amount of seagrass that's there. We had a lot of seagrass at this site, and the hurricane came, and then we had very little seagrass. In fact, that's calcareous green algae. So we had that site, and then we had this site that crashed as well, but then seemed to start recovering. Well, the difference was this one was completely eroded away, and that one was buried. So what we've learned from that, of course, is that hurricanes have a spatial pattern in their effect on marine resources. They also affect different things in the community differently. So in South Florida, hurricanes pull out the algae before they pull out the haliduli, before they pull out the syringodium, and the thalassia is the last thing to lose. So we actually got a change in species composition that was driven by this disturbance, and it varied through space. So fast forward to data from last week. This 216 I showed you, this was the data I showed you earlier. You see that it took until 2012 for us to start getting appreciable seagrasses there again after Hurricane George back in 1999. So in 2012 we started having seagrass, and then there's Irma, and we had basically, this was, you can't see in the room, but this is a syringodium bed, a very sparse syringodium bed. That was in June. October, there's nothing there. It's all been eroded completely away. So in this case, we seem to have a system that it got hit by hurricanes enough to maintain it in a bare sand area. And if we had a longer inter-hurricane period, we'd likely have more syringodium out there. Now this one, remember I said some sites were buried and some sites were excavated. This was a buried site. And what you can see is this was Hurricane George. And then we developed a community. Follow these black. This is the abundance of thalassia, and the patches where thalassia is. And then the thalassia disappeared again. But this site was buried once again. So the same thing that happened in George. We had erosion at one site, burial at another site. And in fact, this is what it looks like there now. This is the sand that's been moved in over that area. And this was a little high spot that still has some grass. So we suspect that this kind of damage will come back much faster than that erosion damage, just like it did in the interval between 1998 and 2017. Okay, so now let me move from talking about hurricanes and the general monitoring program that we have in the Florida Keys National Marine Sanctuary and talk about what's going on in Florida Bay. So we had a big seagrass die-off in Florida Bay in the 1980s that it took us about 10 years to understand what's going on. But what happens is hypoxia kills the grass. Then dying grass drives more hypoxia, and this system grows, and we lose more and more grass. This happened once, as we know, that we knew about in history in 1987, and then it happened again in 2015. But luckily, because it happened in 1987, the FHAP program was established, so we have data and we understand how the system behaves now because of the work that Penny et al. Have been doing. So this was the first paper. So what happens, I've got to go through this really quick. When seagrasses die in Florida Bay, they die in beautifully clear water, and the seagrasses die. You get lots of dead material on the bottom. You get basically the shoots are still there, but the leaves fall off. And then sometime after that, there are some places that survive. And then a couple years after that, we started getting degradations in water quality leading to increased epiphytes and water column turbidity. This is just, there were no data before that die-off. And see, these are chlorophyll, and it took a couple years after seagrass die-off to start getting these big phytoplankton blooms. And I'll go through this really quick. There were knock-on system. The entire ecosystem changed. Sponges died because of the Synechococcus bloom. We lost all the lobsters that lived in the sponges. And then phytoplankton wasn't being filtered out of the water. It was being driven by high salinity and high temperatures. Those high salinities and high temperatures lead to very low ability of the water column to hold oxygen. And when that happens at night, especially when it's warm, when BOD goes up, you get water column hypoxia that causes death of the below ground tissues of the seagrasses. And then when that happens, hydrogen sulfide is made. Hydrogen sulfide is toxic, but luckily oxygen will turn that back into sulfate. I'm just going to click through this really quick, but it's that sulfide that's getting into the meristem below ground that kills the grass. So the FHAP program, I saw Penny run out. I thought I said something to insult her. Thank you. Very good, bud. I'm way over time too, right? So the FHAP program was designed to look very carefully at what was going on in these polygons, and those polygons are defined by shallow bank systems out in Florida Bay. And in each one of those, they dropped a hexagon grid of 30, and then they randomly sampled a site within that, and they've sampled that twice a year since 1995. And not only that, they went back after the die-off in 2015, but then also very recently to find out what's going on with the hurricane and how much the hurricane impacted the distribution of seagrasses in Florida Bay. I haven't received any of those data, so you'll have to ask Penny what they look like. So this is an incredible sampling effort with each one of those points, a place that they sample, and they're measuring cover and abundance of seagrasses as well as other things. And this red basically is the extent of the seagrass die-off in 2015 that seemed to be thankfully curtailed by a very wet, dry season that reduced salinities and reduced temperatures within the bay, and it seems to have slowed down and basically stopped. But the only reason we know that what's going on out there is because of this project that was put in place in 1995. So these are maps of part of the system, and so they're 2015, 2016, and 2017, and how green it is how much grass there is of different species. And follow this. So 2015, this Rankin Lake area, the thalassia died completely. And it hadn't recovered in 2017. But what had happened by 2017 is that system was starting to be filled in by haliduli. And haliduli is now covering the bottom. And I think the last slide, oh no. So this is Penny's model. What we understand, so this is the data in Johnson Key Basin, one of the basins from 95 through to 2017. We had, before this would have been 4s and 5s in the red dots. Seagrass die-off shoved it way down, and then it took 20 years. We got that dense thalassia community back, and then we had seagrass die-off again. So prior to die-off, it looked like this. This overdeveloped system develops a metabolic imbalance. Seagrass dies. It starts coming back, starts growing back, but then something happens and we lose water clarity. Water clarity leads to further loss of seagrass, and then slowly we get haliduli growing in, haliduli and syringodium back to thalassia. So that cycle we understand now because of this long-term monitoring program. And the last slide is pictures from Rankin Lake. And so this is what it looked like in their 2015 sampling. And in October, it looked like that. And then in May, there were some little surviving pieces of grass here and there. May 2016, and by May 2017, it was a beautiful haliduli carpet. And we think that this time that die-off wasn't nearly as severe as it was in 1987, 88. All right, so I just try to give you a flavor for the monitoring that we have going on in South Florida in seagrass beds, and that's all I have. Thanks. Let me see, how are we on time? Oh, and I still have 5 minutes. So, are there questions?
Not really seagrass related, but I was curious if you found any large areas of Caulerpa prolifera out
You know where you find the most Caulerpa prolifera is in about 30 meters out in deep water. We actually keep track of 12 different species of Caulerpa in our monitoring, and prolifera occurs, but it hasn't ever been a weed that's choking out seagrass in the monitoring that we've done across the system so far. And in Florida Bay, we rarely see prolifera. We see Siraculoides and Mexicana, but not prolifera there. It's usually in deeper water. So Peter next.
Yeah, so is this kind of cyclical die-off, is this typical of seagrass systems, or is it something that represents some antibiotic?
So the question in the back was, is this a cycle that we know well from the seagrass literature, or is it something weird? And as far as we know, it never happened in Florida Bay before. If something of the scale of the 1987 die-off had happened in the 20th century, it would have been in the newspaper because there were lots of people working out there. So we don't think it happened in the 20th century. We think what's going on in Florida Bay is the marinization and hypersalinization of the bay has led to a situation where it's an organic matter trap, and you can put very little oxygen in hot, salty water. So there are really no good examples from elsewhere in the seagrass literature that I'm aware of cyclical die-offs of seagrass. We didn't think it was cyclical in 1987. We thought the world was ending. Then I thought the system was all better in 2015, and then it happened again. So now we understand that there is a cycle.
So we're missing marine grazers?
You want me to give my Bermuda talk? Bermuda talk, there's no seagrass left in Bermuda because the grazers have eaten it all because there's nothing to eat the grazers anymore. So yeah, but that's certainly, Jeremy Jackson wrote that the die-off of seagrasses in Florida Bay was because we've killed all the turtles. There were no data to support that, but certainly that hypothesis is out there that we're looking at, no matter what, we have modified food webs because humans have modified these food webs, and when you're looking at the bottom of that food web, it could be affected by the grazers or things that eat the grazers or things that eat the things that eat the grazers in multiple step pathways. Gene?
Yeah, Jim, as you know, I started diving or working in Florida Bay in 1959, and the luscious turtle grass in the whole bay was in Fourqurean Basin. That's where the stuff was that tall, and it was just thick. And then that was the first place it crashed in 1987.
Yep.
It just boggles the mind that would happen where it was the luscious.
Yeah.
What other places in the bay didn't die.
That's right. In fact, salinity and temperature doesn't kill the grass. It's the utilization of oxygen that drives the system hypoxic, and that only happens in places with really high biomass. So across Florida Bay in 1987, there were places where the dense beds would die, and then 40 meters away, the sparse beds would not. So.
And then a question, why do you think that area of Syrengodium is so lush? The sediment's only about that thick there,
Yeah.
and that is the luscious grass anywhere in the bay.
From our kind of ecological, physiological ecology experiments, we know that Syringonium and Haliduli, they have faster growth rates and they have higher nutrient requirements. So we think that that's just a place because of the sluiceway there. There's relatively high phosphorus delivery. We know that from the N/P ratios and other things. So it's a place of relatively high nutrient availability but still clear water column, and so we get the proliferation of this really fast-growing species. And we think that it's out-competing the slower-growing things like Thalassia that would be there if it weren't there.
In that first satellite image you showed, that belt, that black belt, that's all Syrengodium.
Yeah,
And that's the most spectacular thing you see on that.
it's that deep.
Whole image. I've been watching that for years. That much sediment, and then,
Yeah.
of course, as you know, that's where all the lobster divers go
Yeah.
during the lobster crazy season.
Absolutely. So I'm going to have to call my.
Potholes, and
Yep.
that's where the lobsters are.
Yeah, any place you get a little hard bottom outcrop, especially, that's out there.